Meet the next talk, Intro to WebGL with Python Examples, from Łukasz Langa. Łukasz is a Python core developer, Python 3.8 and 3.9 release manager, creator of Black, hobbyist musician, and dad. So let's start the talk.
Hi, welcome to WebGL with Python. My name is Łukasz. These days I work for the Python Software Foundation as the CPython developer in residence. So that's a pretty cool position. These days I work with Serhii Storchaka from Ukraine and with Petr Viktorin from the Czech Republic as a team. So we are just about to release Python 3.13 Beta 1. I highly recommend you test it with us so we can end up with the best possible Python 3.13 release in October. But today we're going to be talking about 3D experiences with WebGL and PyScript. This is an area that I got very interested in last year. That's an example of a game I built for the PyWeek competition in September. I didn't win any prizes, but it was very interesting to me to actually complete an experience from start to finish. And by doing this, I discovered plenty of new knowledge that I never really even kind of thought about existing. So I want to share some of that with you so that you can maybe be inspired to also look into this kind of line of expertise, this line of computing, which I find very rewarding because, you know, it's visible results. It's essentially very flashy. So let's start with something less flashy but very fundamental, which is a triangle. And in fact, I don't want to talk about the entire triangle. I want to talk about this, which is a vertex. A vertex is a point where two or more curves, lines, or edges meet or intersect, and the triangle has three of those. You can see all of them right here, and you can imagine that this is probably the simplest form of a polygon, but there can be more complicated ones, like this one that essentially has 6 vertices, and those vertices form edges, and through those edges you can gonna have some face. So meshes are geometric models that are essentially collections of vertices, edges, and faces, and they represent a shape of a 3D object. And when I was first looking at this, I saw that triangles somehow are used as the building block for those more complicated models all the time. And I didn't understand why. Why not hexagons? Why not squares? I didn't know. So I couldn't find like a great answer right away. So now that I know, I want to share. Looking at a polygon of more than 3 vertices, you might think, okay, this actually looks pretty useful. We might shape it as we need it so that the meshes formed from those kind of polygons might be more, I don't know, like close to the real shape that we want to model, right? But the issue here is that what I'm not showing you is that the actual places in a 3D space for where those vertices are might be somewhat surprising. And in this particular example, one of the vertices is on a different plane than every other one. And in fact, there is no single plane that you can map to those vertices to cover all of them. And this is problematic for, you know, when it comes to computations of 3Ds. So we usually prefer triangles. It gets even better because you can do like the connect the dots thing and imagine what sort of polygon this represents. But if you have more than 3 vertices, sometimes that representation might be really weird, and that would cause essentially rendering issues. Things would look weird. So in the end, we're not doing that. We're modeling everything, including hard shapes like spheres with triangles. Triangles win. Any complex 3D object that you see in GL-based 3D experiences is a triangle mesh. Including here, you can see plenty of tiny triangles on the rim that, you know, try to mimic actually having like a round rim. But this can actually fool us very well thanks to fancy programs called shaders. So here you have a wireframe representation that actually shows you all the edges. But usually we don't use that sort of representation. Usually we only show you the faces of objects. And shading is depicting depth perception in 3D models by varying level of darkness. So programs for the GPU that implement a particular way of shading are called shaders, and that changes what you see here into something more like this, which is way more 3D, right? Now you can see the depth, you can see how the object is really shaped. So shaders run massively in parallel on your GPU, and they implement scattering of light for a set of polygons, and that is usually called materials in the industry. So if you see materials being applied to a 3D object, those are going to be shader programs. And shader programs come in pairs. You're going to have a vertex shader that says, where are the vertices in the 3D space? And a fragment shader that computes the color of every pixel in the currently drawn primitive. This feels like, the golden standard right now, and this feels like this has been there forever. But in fact, like the evolution of the APIs for graphics is relatively recent. OpenGL 1.3, true, that came out in 2001, and then a version that was for embedded systems like phones before iPhone and PDAs before tablets, that was released in 2003. But it only took later and later for us to get the basis to what was WebGL 1.0. That specification was released in 2011, so 10 years after OpenGL 1.3, and in major browsers only by 2014. So the next generation of those APIs ended with WebGL 2.0, which as a spec was released in 2017 and only gained popular support in browsers in 2022. So that is very recent. Obviously, the evolution still kind of continues, based on new hardware that we have and new needs that we might have. In fact, all of this is now being replaced by Vulkan, that is closer to Metal, more in line with how current graphics cards actually work in hardware. And there's also a new API for the web for GPUs called WebGPU. I love that logo since it uses triangles. Like triangles are important. But the reason I'm showing this entire slide is we're not going to be using WebGPU today. This is way fresh of a spec. The support for it in certain browsers is still not extremely popular. So WebGL it is. It's not a deprecated API, it's going to stay with us for a long while, and it's good enough to what we're going to be talking about today. But obviously it's the browser, so it's JavaScript. So how come is this a topic on a Python conference? And that is thanks to PyScript, which is a relatively new project, but already gaining plenty of adoption. And in fact, it's a few things in one. So first of all, you have PyScript.net that tells you, oh, there's an easy way now to package either PyODide, which is a real Python 3.11 interpreter, alongside with micropip that allows you to use third-party packages like NumPy or Pandas, or you can use MicroPython, which doesn't have all that, but it's tiny, so the download time for MicroPython is going to be a tiny fraction from what it takes to start up a PyODide session. So PyScript.net explains that and puts that for you to use for anything that you would like. If I'm not mistaken, it's Apache license, so pretty open. You can use it for anything. And then there's PyScript.com, which is this sort of community of sharing of things with PyScript. And this is commercial. Obviously, like the platform is free, but there's gonna be, I think, some paid features like along, the way here. But it is already, even though it's simple for now, a very rewarding platform to experiment with, since you literally can just stay in the browser and see how the things that you are working on will look like later on when they're deployed. And you don't really need to deploy anything, because once it runs, you can just share a link to the result with somebody else and you're done. So I find it extremely productive and perfect for this particular talk. So I actually moved all the examples to PyScript.com just so that it is very easy for you to look at them later on. So even though we're going to be looking at quite some amount of code from now on, don't worry, you don't have to write everything down. You don't have to be nervous about missing a detail, because it all lives on PyScript.com/@AMBV. So those are my projects right there. So let's start at the beginning by drawing a triangle. And what we're going to be doing here is going to be something you don't want to do normally, which is to use the raw WebGL API with PyScript. No other framework, no other libraries. We're just going to be calling those APIs directly. So just so that you see how that feels like. So that's the editor of PyScript.com. And here you see the index.html, where we can put a script of type py in our HTML and it will run Python. I find that fantastic. To do this, you only need a tiny bit of boilerplate with the PyScript.net CSS and PyScript.net core.js. Relatively little in terms of boilerplate to be able to run this. And now with modern versions of PyScript, you can have an interactive terminal in your PyScript script and also run them in worker threads, which leave up the main thread to do something else, like, I don't know, React or whatever you want. So that interacts with the entire browser application ecosystem extremely well. So I love it. I think the worker functionality here is fantastic. So let's look at some Python code finally, shall we? Our code for now is going to initialize WebGL, which you will find is not an easy process. And then it's going to render a triangle as promised and just print done to our terminal. So it seems like, shouldn't be too many lines, but as you can already see, it's over 100. And the reason why is that the GL APIs are very low level. So first of all, you might have noticed this on the HTML if you look closely, but here you will notice this for sure, because half of the page really is about compiling shaders. So what does that even mean? Well, as I said, to actually do anything on the graphics card, you need to put some vertices there and color the faces, color the fragments in some particular way to actually be able to, be seen on a display. So we have this pair of vertex shader and a fragment shader that form a shader program, and then we can do things to it. So here we set up one and the other, and also find a variable within one of those shaders called a position that is going to be the point of our communication between our Python code and the shader code that runs on the graphics card. So if you're wondering how the shaders actually look like, well, they look like this. I, hid them before in the slide, but now I guess there's no point hiding it from you anymore. It's written in GLSL. So that is a domain-specific language that kind of looks like C, but it's not. And that code runs directly on the GPU. You don't want to write this sort of code directly all the time. You might. There's a nice website called Shader Toy where you can do like plenty of very impressive computation with just shaders alone. But for us, we want to do WebGL with Python. So this is just a boilerplate that is needed, because without the shader program, nothing can be displayed on the graphics card. So the shaders, even though you might not see this, are very simple here, because we're literally just putting the vertex positions that we're getting from our Python code wherever the Python code says they should go, and we're not doing anything else with them. And the fragment shader is coloring that, figure, coloring that polygon into some reddish purple. That's from WebGL fundamentals. That's, for whatever reason, likes this color, so I kept it. Right, and essentially even creating the shaders that I used helper functions for is not terribly easy here. What is nice is this is Python code and we're calling WebGL, so awesome, right? But you know, it's pretty verbose, to be honest. So we're not going to be doing a lot of those things later on. We are going to be using some higher level API to do those things for us, so we can actually you know, focus on more interesting experiences. But for now, I actually wanted a complete example that you can go to and look at on PyScript.com, where this is actually just raw WebGL with Python. So the render is the actual interesting part where we are putting some vertices in. And even this is a really low-level API where there's an array. As you can see, it's single dimensional despite the formatting, but we are telling it later on that you should take 2 components per iteration and they're going to be representing some vertices, right? So you configure how WebGL is supposed to read the data we give it, and this render essentially puts that into the GL draw arrays call, and that's it. We end up with something that appears on the screen. So how does it look like in practice? Let's see. It loads, and it is here. There's a triangle. Quite a lot of work for something that small, right? So you can see the render, the initialization, and the print. There we are. The positions here might look kind of weird to you, but that's because in this coordinate system, 0, 0 is in the middle of the plane. So -1 is to the left or up, and 1 is down and right. So kind of weird, right? So in here you have the first point is the top left one, the second point is the rightmost one, and the third point is the low one. So we can change our code to be a little more interesting here, and let's utilize just some Python knowledge right now. That might not be the best way to do animation in WebGL. In fact, like I know for a fact it's not, but let's just use async IO, because why not? If you add async to the script tag in your index.html next to worker and terminal and so on, you can put await on the module level here, as we're doing. And here, I don't really need async IO, but I wanted to show you that, hey, async IO works with this. So just imagine the possibilities. And here, the possibilities are rather basic. I just wanted to animate something, so at least the payoff would not be so trivial. So here we are actually utilizing the power of Python to animate our triangle on the graphics card. So I guess that's pretty cool. Right, so moving on from this low-level thing, what we would want to do is actually do some 3D. And you might have noticed that there is no 3D here at all, because, as I discovered, WebGL and also OpenGL are not 3D frameworks. They are rasterization engines, which means they take some points, lines, and triangles and just put them on some bitmap somewhere that you can then display on your screen. But if you want to build 3D on top of this, well, that's on you. So we're going to be using a framework called Three.js, with which we will be interacting as Python developers in the browser to implement all those building blocks for us. We don't want to implement all those fundamentals that every game engine needs to do to display a sphere or whatever else in the 3D space. There are some functions that I call here on line 11 and so on that demonstrate some basic building blocks of a 3D world. So first of all, the scene is all objects that can potentially be visible. Camera is how we look at the world. Some cameras are using perspective, some are different, like, I don't know, like an isometric one will not actually have a perspective that has 2 lines that meet in the horizon. It'll be more kind of mathematically parallel and so on. So the camera sets everything up for that particular thing. And also it says how far into the distance you can look and so on, and what your viewing angles are and so on and so on. The render is in fact what puts the camera's view frame on an HTML5 canvas element, since in the end, this is where everything gets drawn. It can be part of your HTML, like either put dynamically via JavaScript or already there in your template. But in the end, this is what you need to do. There's going to be a canvas element that we're drawing on. Controls is how we interact with the 3D experience. Making controls like a mouse or a keyboard or a game controller interact with your 3D world in a way that feels natural is actually complex math. So I'm very happy that Three.js provides this for us, so we don't really need to do much work there to make sure that users can interact with our experiences in a meaningful way. Lights are necessary for there to be anything visible because they project illumination that cause materials on objects to react to reflecting light somehow. And the stats is just an FPS counter. So the initialization here is going to generate 50,000 cubes and two lights. One is green and actually emits light very far, and the other is white and it only emits light close to us. And as you can see in the animation frame here, we generate animations frame by frame, and each of those frames will move our camera position across some circle. Like a sign is a perfect example for this because it's going to look nicely. And then we're actually moving our lights with us. So in fact, they are attached to where we are. And this is done such that you will always have the closest objects illuminated white and the ones that are after illuminated green. And then we render actually the scene with the renderer and request another animation frame from the browser, which means the browser will tell us, okay, I'm ready now for another one, and it's going to call us back. To do this, we need to create a proxy with a JavaScript object. I'm not going to go into details why you need to do this. It kind of is related to our life cycles with reference counting and, you know, how long certain things need to stay in memory for JavaScript to be able to reference them. So how does this look like? Starts a little slow, but then you actually have the 3D experience, which maybe is somewhat basic, but it's already pleasing to the eye, like if I dare to say so myself. And then you can also use your mouse, because we have controls, to interact with it. So see, you can drag and change your position in a meaningful way. I find it pretty pleasant. As you can see, the experience here is not like, you know, very high FPS, but that's mostly because I'm recording this at the same time as we're talking. So it would be a little better if we didn't have all those extra processing that I have right now. Right. So just so you know, the Three.js APIs are relatively straightforward. They are high level. This is why I'm showing you this, not for us to actually discuss what the perspective camera is and what not, or how the WebGL render is configured. For all of this, there is plenty of awesome documentation on Three.js.org. And you might be a little weirded out that, okay, but this is JavaScript documentation. But let me tell you that translating what you see here in those examples to the Python code that you write in PyScript is essentially maybe not trivial because sometimes there's gotchas, but it's natural. And after a while, I've become pretty comfortable with it. So just having a mature framework like this is godsend. I love it. So now that we moved on from Three.js, we can see how we should set this up. So you might be wondering, okay, but how do I actually import a JavaScript library that you need to reference somewhere online? Well, how do I do this? Well, okay, good question. There is a bit of a trick here for this to work. So I'll just put this on the slide so you know to actually look for it on PyScript.com later. There's going to be an import map where you need to actually reference what you want to import. And then there is a little bit of boilerplate that I'm using such that Python code will see those new style JavaScript modules. What we need to do here is essentially to kind of inject those new style JavaScript modules into the old style global this namespace. So we're doing this just so that the code can actually import things from 3 or trackball controls or so on or so on. So you might be a little overwhelmed by the complexity and underwhelmed by what we've done so far. So let's do something a little bit more flashy here. So in this particular example, there's no animation other than what you're doing with the controls. So the controls, the user interaction will drive the rendering. You might have noticed that, you know, we need to create those JS proxies here as well. And I use the create proxy as a decorator. And that's because we need to issue some callbacks. We're going to be looking at those in a while. But the interesting bit here is that the render method is almost non-existent because the scene is being rendered as seen by the camera, and the camera is configured by our controls, and there's nothing else for us to do, but it's still plenty interactive. So let's look at some more code. The texture callback and the model callback essentially are setting up some details about the first one, how the background looks like, so the environment of our 3D space, and the model callback is what we're going to be doing with the Python logo. So what we're going to be doing is actually compile it with our renderer and add it to our scene, so we can actually just look at it from all directions. You might have noticed that we don't actually have any lights here, and this is because in this magic example, we're using an HDR image where its luminosity is implicitly being used as a light source for our environment, which I found to be extremely cool. So this is a 360 photo that we're using, so you can essentially just look around. And then what? There is a bunch of other 3JS APIs. You've seen some of them before. The controls are a little different. We're just orbiting around that particular center point, which is the logo. The stats were there already. Oh, and the interesting bit is to actually show where the callbacks get called, which is loading the texture is using the Radiance HDR loader called RGBE. And then the model is GL transmission format, which is Khronos's royalty-free spec for data and loading efficient 3D scenes and models. So pretty cool. I found a free Python logo model. We're going to be using that to display it. And the model contains not only vertices, but also edges, faces, and the color, texture, and information about roughness of the surface. So how does that look like? You can drag it, and you can see how light is reflected on the surface, which is not perfectly, glassy. So I find that pretty cool. And you can see this is a shadow because the sun is actually on the other side. And that actual sun, the real sun, is illuminating this virtual space. Yeah, we can kind of zoom in, zoom out. We can move around. Like, I could do this forever. Like, this is extremely fun to me. I find this sort of thing, very cool to be able to do in Python. But if you are still saying, man, but like, this is just a toy. Like, I want to do something real where I have some data, I have something where I can actually use this for work. You can use 3JS totally for work. But what you can also do is to use some even higher level framework like DeckGL. So this is a variant of an official PyScript example that I modified somewhat. It's a reactive application with panel and param with data from a CSV with taxi ride information from Manhattan. So it uses panel's DeckGL output, which is an even higher level API than what we've seen so far. And, it allows us to work fully in Python. Documentation is in Python. These are Python frameworks. So, wow, like, mind-blowing. And yeah, the way this looks like is pretty professional, right? Like, you can actually look through how this looks in time. You can change some parameters there. Like, let's just stop a while and see you can go inside and click on a thing to see the actual rides, where they originated, where they went. And if I'm careful, okay, we can actually see some data point with, oh, somebody was really stingy on the tipping here. But you can see all the things in the CSV, change some parameters. So it's pretty cool. Yeah, so that is also WebGL on the kind of low-level side of this. All right, that's what I have for you right now. What I wanted to share here is the excitement for discovering a new way of using Python, but also to understand computing in general a little better. What you need to understand is this nihilistic world we live in right now that says everything is going to be solved by computers. We don't really need to even have to program ourselves anymore because there's copilots and generative AI that draws already better than you will ever draw and sings better than I will ever sing. Like, all of this is sort of negative, and I find that understanding something on a deeper level will always be useful, it will always be valuable, but mostly for me it's just fun to understand the world around us a little better. And if you've ever seen a movie in a cinema these days, and you've ever played a game or seen like a 3D visualization or looked at a billboard, there was some 3D there for sure. So playing with that using Python is an amazing treat to me. So thank you for your attention. And now I'm open for questions. Let's see if I still have the same t-shirt on. Like, probably not, since I'm recording this on a different day. Secrets. You can find all the code on pyscript.com/@ambv. Let's have the questions now.
Łukasz, hello.
Hi.
Oh, hi. You just told all secrets, right?
Yes.
How are you doing?
Well, we're pretty good. It's not terribly sunny today, but we've almost had summer now in Poland, so I'm actually happy for the rain that arrived.
Oh,
But yeah, all good. It's a pleasant Saturday morning here.
do you like more like rainy weather? Or no?
I do enjoy when the weather is not too cold or not too hot, so I don't mind
Okay.
rain. Like if you have decent clothing, like it doesn't really matter.
Yeah, okay. I just wanted to tell that pretty cool that you are participating in Python 3.13 release. And maybe can you share what kind of challenges you have during the preparation for release? Maybe something goes not in that way that you expected.
Well, it is a complicated release, like in comparison to many previous ones, since there is a bunch of long-term projects that are now seeing the light of day in this one version. So after sort of a lot of work building up to having a JIT in Python, now we are actually getting to the point where we're going to get the first release with an experimental JIT. But at the same time, we're also getting the first release where we're going to have an experimental edition of Python without the global interpreter lock. And also, at that very same time, we're making other improvements to performance of Python and to how it works internally. So all of this, all of those features together make for a complicated coordination. We're now going to have first-class support for building on iOS. So I had a talk on EuroPython, I guess it was 2022, where about like how you can embed an iOS, well, embed Python in an iOS application. It was sort of complicated back then. Nowadays, it's going to be easier. So all of those things combined, like, make for a release that is a kind of one of the most fundamentally, different from the previous one than I've had in years. So yeah, it's not very easy to like make sure that all of those things don't step on each other's toes. But I'm very happy to see the progress and the development there.
Oh, wow, cool. So is it the most difficult? Am I just did I understand right, or just because different, that is why it's difficult?
Well, just getting the removal of the global interpreter lock right is like a very fundamentally complex process because a lot of internals of Python, not just the end user code, but also how Python is built itself, relied on there being a global interpreter lock. And now with it removed, you have to introduce thread safety considerations to a lot of the building blocks. And it just so happens that the work on the just-in-time compiler also for a while relied on there being a GAL for their locking purposes, because if it was there, it was, you know, smart to use it. And now when it's optional, so you cannot rely on it being there all the time, like this complicates the two designs, and they're sort of, you know, having like a tug of war in certain areas. But ultimately, what we're going to get is like a big leap in the design of the interpreter. So yeah, it's a complicated kind of development process, and coordination is required for this. I was sponsoring the PEP 4 removal of the GAL, which is PEP 703, making the global interpreter lock optional. Like that PEP was written by Sam Gross, who actually proved the concept of removal of the GAL and also spearheaded actually doing this change. Like from the meta side, he contributed a tremendous amount of code and, you know, kind of also direction. Like he's very active, like on our forums and the issue tracker, actually talking with other people how all those things are supposed to work together. Brant Booker, working on the Faster Python team at Microsoft, wrote a PEP, you know, around the JIT. So that's PEP 744. Like funnily enough, like that PEP essentially was written after the JIT was landed in Python, but you know, well, like we now have those two design documents, like they're still evolving as Python is still evolving. Beta 1 is early May, so there's still like a few days left for us to land some more changes there. But fundamentally, we already sort of know what Python 3.13 is going to look like at this point.
So see, you just told more secrets, more your secrets. Okay, so you know, like all these processes, like when you are participating like a release manager, I think that it's like a case for you, and maybe there are any your favorite features in that releases that you made in Python. It's like, what is your
I
favorite
mostly,
feed?
oh yeah, so like this is something that we've been actually talking about since when I started working as the developer in residence. It didn't really pay much for me to work on features of my own and on PEPs of my own, since those are very lengthy processes. And instead of doing that, I can be more productive, like unblocking other contributors. For example, making sure that the automation that we have in our development process, the bots and everything, like that stays functional and does what we want it to do. Similarly, when we have build bots, so like our CI, which is you know, figuring out whether Python still works after changes that we just made, making sure that this is green and making sure that this is at least actually running, so actually actively testing, that had more worth for us. So for example, we, at the time I started, didn't even have a single machine that would run big memory tests. There's an entire category of regression tests that we have that require more than 20 gigs of memory, right? And for those, we didn't have any machine. It's very expensive for them to like land them on AWS or somewhere. So we didn't have one box that would actually run those tests. So, you know, secret, actually, there is one right behind me. Like here, you can see like that's a big memory build bot for Python that I built, and it's not only doing regression tests for us, but also it's a Windows machine. So again, something that we didn't have enough build bots for. So I focus on stuff like this. But now we actually do have more team members, right, with Serhi and with Peter. So we were discussing that now we also can now pursue some longer term projects of our own. So yeah, like I intend to take this on, but this is going to happen after 3.13 beta 1, since now just in what, 20 days, I'm leaving for PyCon US in Pittsburgh. And there I have talks, and there I organize Language Summit and whatnot. So I'm kind of focusing on this right now. But yeah, after we're back, there's definitely going to be some features. I'm seeing async IO and typing, like that are my kind of usual, darlings. I'm going to be focusing on those areas.
Mm-hmm. Yeah, I understand. Like this, all conferences, like you cannot not just to participate in this because it's just a part of your life.
Yes, exactly.
Okay. I remind to participants that please don't hesitate to ask more questions in Discord, and Łukasz will answer them there.
Yes.
And Łukasz, thank you so much for an interesting talk and for joining us today. I wish you the best of luck in the new Python release. And
Thank you.
yeah, let's continue in Discord and hope to see you someday in Kyiv when it will be safe, when everything will be fine. We really hope for this, to gather everybody offline and international speakers as well.
All right. Thank you very much for having me.